Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper from the Hugging Face trending list, published on October 9th, 2025, about 2 days ago. The standout result is a linearizer architecture that makes a conventionally nonlinear network exactly linear in learned coordinates, which lets diffusion sampling collapse to a single step with mean squared error of 3 times 10 to the minus 4. The paper is titled, "Who Said Neural Networks Aren't Linear?" And as we'll see later, the implications for training and analysis are quite significant. Beyond one-step sampling, the work unlocks SVD and pseudo-inverse tools, supports exact composition, enables idempotent generative models, and even modular style transfer. Alright, the intro set up the big idea. Figure 1 shows the overall layout, with the model as a linear block wrapped by two invertible maps, which makes the mapping exactly linear in learned coordinates. The left panel depicts x flowing through gx, then a matrix A, then gy inverse to yield y. The right panel illustrates the induced vector space rules. Addition encodes both inputs, adds them in latent, then decodes, while scalar multiplication scales in latent before decoding. While Figure 1 laid out the linearizer mechanics, Figure 2 shows side-by-side samples, contrasting multi-step flow matching with the collapsed one-step variant that replaces many updates with a single operator, so the visual quality should match. The left half presents menace digits under panels A and B, which look essentially indistinguishable. The right half presents Celebi faces for the same comparison, which also display matching details and diversity. So, the previous figure showed that multi-step and one-step sampling matched visually. Figure 3 illustrates one-step inversion, interpolating in latent space between two real endpoints, so intermediate images transition smoothly. The left red box column marks x1, and the right red box column marks x2. The gradual morphs across digits and faces indicate a straight path in the learned coordinates, which becomes a curved trajectory after decoding. This behavior supports the constant velocity view that enables a single collapsed operator for generation. So the previous figure illustrated smooth latent interpolations. Figure 4 presents quantitative checks that back that up. The left panel reports FID across step counts, where the one-step score matches about 100 steps and improves by roughly 8 points when simulating 1000 to 1. The middle panel shows inversion consistency, with peak signal-to-noise around 32 to 33 and LPIPS near 1%. The right panel compares 100 versus one-step fidelity and remains similarly close. Alright, the previous figure reported quantitative fidelity. Figure 6 shows how idempotent generative training works and what it produces. The left panel depicts x passing through G, a binary diagonal matrix that acts as a projector, and G inverse, with a straight-through estimator so gradients flow despite hard zeros and ones. The right panel presents inputs on top and projected outputs below, which stay on the target distribution, because applying the model twice equals applying it once. The sparse and reconstruct losses tie the operator to a tight manifold while preserving content. So the previous figure showed idempotent training and its projections. Figure 5 presents modular style transfer, which treats each style as a matrix acting in the learned latent space so styles can be mixed by simple linear blending. The left column contains the original content images. The middle columns show two stylized endpoints that come from different style operators. The long sweep on the right displays smooth interpolations between those endpoints, confirming that linear mixes of operators yield gradual, coherent style transitions. So the previous figure demonstrated modular style transfer in action. Table 1 summarizes the block flow for the two backbones used throughout, which are diffusion and style and IGN. The diffusion and style stack applies optional squeeze, then act norm, two affine couplings, and an invertible 1x1 convolution, and this sequence repeats 6 times. The IGN stack splits space into two streams, uses additive couplings with shared functions, concatenates, then pixel shuffles for reversible down and up moves. Alright, 2 takeaways stand out. The linearizer reframes a nonlinear network as exactly linear in learned coordinates, and that unlocks the full linear algebra toolbox, from pseudo-inverses to singular value decompositions. The broader implications are faster sampling, stronger controllability, and analyzable structure for generative and editing tasks. Thanks for joining. That is it for this episode of the AI Research Roundup. I am Alex. Thanks for listening.